Welcome to Naked Reflections, brought to you from the Wolf Institute. I'm Ed Kessler, and each week I'll be taking an in-depth look at the stories reported by our friends over at the Naked Scientists. What does the latest scientific stuff mean for the rest of us? Stay with us and find out. E equals mc squared. It's probably the most famous equation in the world, and the guy who figured it out, Einstein, is probably the most famous scientist in the world, even 60 years after his death. Indeed, he seems almost to personify the idea of genius. Here's the actor David Tennant celebrating the 100th anniversary of the publication of Einstein's general theory of relativity on the Naked Scientist podcast.
At 26, he figured out nothing less than a new theory of space and time. It led to a nifty way of simplifying physics by treating space and time as one thing, space-time. But Albert was just warming up. He wasn't happy with Isaac Newton's mysterious force of gravity. Naturally, he started work on his own theory. And sure enough, he cracked it. Mass causes space-time to curve. The natural motion of things is to follow the simplest path through space-time. But since objects with mass curve space-time, stuff moves towards the most massive object. That's what you feel as gravity. It's warped space and time that's keeping your feet on the ground.
So we're talking about Albert Einstein this week, and the way that his work brings scientific inquiry alive, even for scientific ignoramuses like me. It makes him the perfect subject for a Naked Reflections discussion. My guests this week are Dr. Michaelis Agathos, a research fellow at the Kavli Institute for Cosmology and the Department of Applied Mathematics and Theoretical Physics here at the University of Cambridge. I noticed, Michaelis, that you're an active member of the LIGO-Virgo collaboration. What is that?
Right, that is true. So the LIGO-Virgo collaboration is a collaboration of scientists that work on the current gravitational wave experiment across the world. So currently there are three operating gravitational wave observatories, two LIGO observatories in the US and the Virgo observatory in Italy. And since 2015, we have successfully been detecting gravitational waves.
And our second guest, Dr. Richard Staley, Hans Rausing lecturer and reader in History and Philosophy of Science here at the University of Cambridge. Richard also, helpfully, is the author of Einstein's Generation, The Origins of the Relativity Revolution, which we'll hear more about, I'm sure, and leading a research project intriguingly titled Making Climate History. Richard, what's that about?
Oh, that's really taking a long-term look at the history of climate change. I mean, climate change is obviously one of the most important issues that we face at the moment. And a lot of our thought sort of oscillates between the last 20 or perhaps the last 50 years and the next 20, 50 years. We want to look at the history of climate change from around 1800 onwards and really get a long-term structural perspective, particularly on the relations between making and knowing. We think that we know more when we make things, and this is a very interesting question in that regard.
Well, we might come back to that and see where Einstein fits in, but I'd like to start with a very basic question. What about Einstein's celebrity status? It does appeal in some ways. Is it a helpful stereotype or is it just foolishness? Richard, what do you think?
Well, I think Einstein really was one of the first scientific celebrities. If you recognize that this really occurred in the age of mass media, with the rise of newspapers, radio, and in particular in the context of the post-World War I environment, where he emerged as a figure who controversially could unite warring countries. And that question of controversy was very important in understanding his early celebrity. And that's celebrity in a public sphere, unlike the kind of celebrity that Einstein himself had faced as a scientist. When he first moved to Berlin, people came knocking on his door and asked to interview him and so on. He was already being compared to Copernicus. But that was quite different from disembarking on a ship in New York and having crowds of hundreds of people waiting on every word. And that rise of celebrity as a scientific celebrity as part of mass culture, that's really distinctive to this post-war period. And there's an interesting feature of the relationship between Hawking and Einstein. When Hawking's A Brief History of Time came out in 1988, it had a very short biography on the back cover. It went something like Stephen W. Hawking was born on the 8th of January 1942, the 300th anniversary of Galileo Galilei's death, and he holds the Lucasian Chair of Mathematical Philosophy formerly held by Sir Isaac Newton in the University of Cambridge. And when I read that, I thought it only needs to finish and will die on the anniversary of Albert Einstein's birth. And in fact, that's what happened. Hawking died on the anniversary of Einstein's birth.
When I looked into Einstein in a very general way, I was shocked that he was such a slow developer. I read that he only began to speak at sort of the age of 5 or 6, and then he worked, I couldn't believe it, as a Swiss patent officer. What's going on there, Michaelis?
Yeah, so there is this story about him being a slow speaker. He would actually spend some time reciting sentences by himself quietly. He would get the courage to speak it out loud. An element of his personality, an introvert element of his personality. But later, of course, he became more confident as he grew. And his early years were in his early years, he saw a fast transition from the rather timid and kind of reserved child that he was to more outspoken and charismatic personality later on in his life.
And his breakthrough year was 1905. What happened then?
So in 1905, what happened was actually his entire career can be kind of characterized by long gestation periods of deep thinking over difficult open questions, and these periods would usually be followed up by a magnificent burst of productivity. And 1905 was the first time that this happened. And in this year, he published, I think, about 6 papers, very important ones. The 2 papers were famously formulating the special theory of relativity, his first revolution. But at the same time, he was quite influential on the other revolutionary theory of the time, which was emerging, which was quantum physics. So his other papers were on things like the Brownian motion and the light quantum. So one of his papers was actually solving the problem of the photoelectric effect. This is the effect that also got him the Nobel Prize about 15 years or so later on. And this was a purely quantum phenomenon. It was a puzzling question of the time.
Well, help me understand that breakthrough. What is this special and general theory of relativity? They're 2 separate papers that he wrote. And Richard, I think it was the special that he wrote first and then the general a few years later?
Yeah, that's right. The theory of special relativity came out in that 1905 burst that Michaelis was talking about. And it was really concerned with solving problems in the electrodynamics and optical theory of the period, which was all about the curious fact that the conceptual framework that came from Maxwell presumed an ether at rest. But we know that the Earth is hurtling through space, and trying to understand how to reconcile a rest ether with motion through the ether and get a similar result was really at the core of this special relativity revolution. And what he was concerned with there was reconciling the problematic sort of features of different principles that appeared to be in conflict with one another. And he showed that you could resolve those conflicts if you recognized that when you measured time and space, you had to take account of the frame of reference in which you were working. General relativity moves beyond that In special relativity, one is concerned particularly with inertial frames of reference, moving at a uniform velocity in relation to one another. In those inertial frames of reference, then the laws of physics are the same. General relativity was considering acceleration and gravitation. And there's a famous thought experiment where Einstein realized that a man falling wouldn't feel his own weight, and was led from that to recognize the intimate connection between acceleration and gravitation, and try and develop a mathematical theoretical framework to encompass both of those. And he did that by developing new concepts of the curvature of space and time through mass.
Okay, let me stop you there because my head is already bursting. Now, I'm just a simple theologian, and in my own studies, whether it's about religion or about scriptures, you often have images of people, images of action, images of the divine. And one of the things about Einstein that struck me was that he was very good at creating these images. So one talks in these very technical terms of relativity, simultaneity, special theories, general theories, and so on. But yet when he created this image, the one I'm thinking of is the clock tower in Bern. You know, we can all imagine what a clock tower looks like. And somehow he was able to translate something incredibly complicated and technical into something very simple. And that's a real gift, isn't it? A gift of explaining things.
It really is. And I think there's something more I'd say about that. One of the things that I find most interesting about Einstein is that his thought experiments have bodies in them. It's a man falling, or it's the idea of if you move along with a light wave, what will you see? And so there's a real sense in which his imagination is embodied. And interestingly, we learn about those thought experiments many years after the work itself. When he describes the work itself, it's completely in a mathematical formulation. It's talking about frames of reference moving. So he works in both those registers. But I've often wondered whether physicists now have the same embodied imagination, or their imagination is attenuated, or works more strongly and more deeply in mathematical structures than Einstein's did. That's something I'd actually like to ask Michaelis if he has any thoughts on that.
Right. This is actually, yes, I agree that this is probably one of the more singular features of Einstein's personality as a scientist, that he was able to perform thought experiments into great depth, and he was able to kind of create these images that help with a deeper understanding of things. Now, I think as we go on in the later 20th century and the 21st century, things in theoretical physics become much more mathematically involved and much more technical. And the problems become, harder to understand if you're not an expert in the field. But there are still analogies that are being used and are very helpful in understanding concepts about mathematical physics and geometry in particular. So I think this has continued to more modern times, but it's probably less dominant in this case.
You're listening to Naked Reflections with me, Ed Kessler, and my guests this week are Richard Staley and Michaelis Agathos, and we're talking about Einstein. To say that his theories have stood the test of time would be putting it mildly. Here's Professor Jerry Gilmore from the Cambridge Institute of Astronomy speaking on the Naked Scientists.
It turns out that general relativity has been tested to astonishing precision. And every single test we've done of it over the last 100 years, it turns out to be dead right. It's truly remarkable. So the whole subject of black holes in space, all these wonderful things we take for granted, X-ray astronomy, massive exotic events, quasars, these are all extreme versions of general relativistic phenomena, none of which happen under Newton. And every single day astronomers are studying things that just exactly follow general relativity. So we know it's accurate as a description of the solar system around us, to much better than 1 part in a million.
Michaelis, it sounds like Einstein's theories are still very relevant, are still true today, and that's the case with your wave studies?
Yes, and I was kind of excited to listen to Jerry Gilmore's quote, and I think looking at the date, I got actually shivers down my spine when I saw the date, because it was actually the time when during which the people in the LIGO-Virgo collaboration were secretively working towards publishing a paper where they would announce the first ever detection of gravitational waves. And that was back in 2015. So what happened in September 2015 was that after a very long 4-year upgrade, the LIGO detectors in the States started their operation again in an upgraded configuration, and that allowed for the first ever detection of gravitational waves. So gravitational waves, I'm going to stick to the established cliche here. You can imagine them as ripples on the geometry of space-time. So you can think of ripples propagating outwards on a calm pond where you throw a rock in it. So the rock represents something very violent that happens in the middle of this, and then you have waves of curvature of space-time propagating outwards at the speed of light. What happened in the middle of this, so the very violent phenomenon that took place, was two black holes of a few tens of solar masses each coalescing with each other, so orbiting very closely close to each other, and then finally merging together. And this ended up with a huge emission of gravitational waves that would reach us in 2015. So the universe has always been vibrant with ripples like this in the space-time fabric, and this conveys information from the most violent events like the collision of black holes or supernova explosion. So what happened in September 2015 is that for the first time, we were sensitive enough with our detectors to be able to pick up these tiny vibrations that the gravitational waves would induce on the space-time geometry. So, the dimensions of space-time would stretch and squeeze ever so slightly. And finally, 100 years after the prediction of gravitational waves by Albert Einstein himself, we were in the position of detecting them for the first time.
Well, that sounds like it was a very exciting moment. Richard, one of the famous Einstein quotes is, "God does not play dice with the universe." Of course, as a theologian, I was quite attracted by that idea. Would you say that Einstein was a deist or an atheist? Where would you put him in the religious quantum?
Well, he's certainly not an atheist. In fact, he said, "I'm not an atheist." And you can see that with that tendency to go towards God and to speak about God when he's thinking about questions about determinism and the like. I'm perhaps not enough of a theologian to say with all that much subtlety, but I do know that he declared himself to be an adherent of Spinoza's God. And that was a God that doesn't take personal fates into account. It's not a personalized God that he's talking about, someone who reaches into our own affairs and the affairs of man, but a God of harmony and of the natural world. And there he really had a very strong sort of sense of the intelligence of the world and quite clear ideas about how he thought that should play out and manifest. One of his criticisms about quantum mechanics was that he felt quantum mechanics wasn't complete. It didn't give a complete picture of reality. And I think that sort of sense of a need for a complete picture of reality does actually relate a bit to this religious sense that he had.
And I suppose that's why Niels Bohr would react against him, because wasn't it the Danish physicist who complained to Einstein, told him off for telling God what to do or what not to do?
Yeah, that's right. There's a very interesting, quite long-term discussion between Bohr and Einstein. And it's one example of just what a great thinker that Einstein was, and also what a stubborn thinker he was. In a certain sense, he retained the concern with linking relativity and quantum theory that he'd had, in fact, in some ways, from 1905. He kept coming back to questions that he'd begun with there. And so he became a critic of quantum mechanics, but quite definitely pushed people working with quantum mechanics to sharpen their understanding of the nature of the theory that they were working with.
Michaelis.
Yes, I would just add, yes, I also agree that he was definitely, well, he was definitely not religious in the strict sense, but he certainly seemed to believe in some sort of like natural order or harmony of nature. Um, and going back to the God does not play dice statement, that we should remember that he was a really central figure in the development of two revolutions. So one was relativity theories, and the other one was quantum mechanics. And these two theories ended up being the most successful theories that we have for matter and for space-time. And they are still at odds with each other. So they are still incompatible with each other. And they are so in a fundamental level. General relativity, and is what we would call a classic theory. There is causality. There is what Einstein was a true believer of, strict causality. If you have initial conditions, if you know the initial state of things and you know the laws of nature, then you can actually predict what will happen next. On the other hand, quantum theory is a probabilistic theory. There's no determinism. There's no strict causality, as he would call it. So, Richard is right. He was under the impression that quantum theory was, of course, at its early stages then, but even later on, he had the impression that it was going through an adolescent phase, and this is just a phase; it will pass. Determinism will prevail at the end. There are things that we are not yet aware of, maybe we haven't figured it out yet, and those things will complete the picture.
It sounds almost like eschatology, that it will be sorted out in the end. When I tweeted about this episode of Naked Reflections, and I asked for help, what did the followers of the Wolf Institute or have to ask you as scientists? And this was one question. Were Einstein's ideas the beginning of the end of the long-standing pre-perception that there is an objective way of things? In other words, I suppose this comes to this question of determinism. Richard?
Yeah, I think I would say that they weren't the beginning of the end. That in fact, Einstein's own concerns were very much with understanding the framework within which you had to understand measurements and physical theories and the like. But there is this fantastic, extraordinary sort of quote when he first becomes well known, and there are London Times headlines about his theory. One of the interesting things about the first headlines is that they talk about the Newtonian theory being overthrown by the Einsteinian revolution. And when Einstein himself is asked to deliver an article for the paper, the headline that it runs with refers to Einstein's theory and the Newtonian system, and he makes it clear that he believes that Newtonian physics will always stand at the foundation of natural philosophy. But he does finish with a joke, and the joke is one about the other kind of relativity, a philosophical or cultural relativity. And he says that at the moment in Germany, he's understood as a German man of science, and that for the British, at the end of World War I, he's thought of as a Swiss Jew. And he notes that if the circumstances were to change just slightly, if he becomes a bête noire, then it will be reversed. And English people will think of him as a German man of science, and Germans will think of him as a Swiss Jew. But of course, it was deadly serious. He had, in fact, already faced anti-Semitism. He was already defending his theory from people who were responding to him primarily as a Jewish physicist. So he understood just how strong and important chauvinism is, and how much it can affect intellectual attitudes even. And so he was concerned with cultural relativism as well, and understood that one had to work against both, work against that while upholding the objectivity of science.
And actually, when you read some of Einstein's more general writings, as I've done, it does come across as very Jewish. The humour that just came out in that telling, Richard, was a very Jewish So he lived through the First and Second World Wars. He witnessed the horror of the Holocaust as a Jew, but also the potential of mass global destruction, and joined the anti-nuclear movement. Was that a reaction to what he saw, or was that also part of his scientific endeavour?
It was quite closely linked to his scientific endeavour, I think. One of the interesting things about his experience in going through World War I was the shocking finding that scientists and artists both actually turned against internationalism. And he worked quite strongly for internationalism in the course of World War I, but failed to persuade his friends to, for example, join the book that he wanted to have with contributions from people from neutral states and from the warring states. And he sent out this idea asking people to contribute, and they all said it's a nice idea, but we don't think this is the time. And when World War I ended, he basically decided to work both scientifically and politically, and to stand up for the politics of internationalism. That was a battle too, but it was one that was increasingly won amongst the scientific community.
Well, we're drawing to a close, and I have one final question for both of you, which was, if you were at dinner with Albert Einstein, what sort of company would he be? And in particular, I will start with you, Michaelis. What would you ask him?
I think he would be slightly disappointed by the persistence of the principles of quantum theory, and the fact that from a conceptual point of view there have not been as many developments in understanding very deeply quantum physics, the principles of quantum physics, and reconciling it with general relativity. So yeah, I'm not sure whether he would like what he saw, and surely he would have novel insights towards a different direction in reconciling the two. So if there was one question that I would like to ask him at dinner, it would be, when do you think the first evidence of general relativity breaking will show up? Because eventually it will have to be replaced by a unified theory that is compatible with quantum mechanics. So when is that? Is that by observing a black hole, or will it be far into the future?
And I think I'd probably pick up on that conversation and want to ask Einstein if he still thought that Newtonian physics would provide the conceptual foundations for physics in the future, or even that relativistic and quantum mechanical thought from the early 20th century would provide the foundation for physics in the future. I'd ask him whether or not he thinks that really fundamentally different conceptual approaches are possible.
Well, I feel as if I'm on the horizon of a black hole and about to tip into an abyss. That's to say, we've reached the end of this podcast. Perhaps I could leave you with this quote I found from Einstein that's really stayed in my mind. He who can no longer pause to wonder and stand wrapped in awe is as good as dead. His eyes are closed. My thanks to our guests, Richard Staley and Michaelis Agathos, and thanks to you too for listening. If you'd like to get in touch with any comments, thoughts, or reflections of your own, you can email nakedreflections@wolf.cam.ac.uk. Let us know what subjects you'd like to hear more about and how you'd like us to cover them. We'd love to hear from you. In the meantime, you can find more episodes of Naked Reflections and subscribe to the Naked Reflections podcasts wherever you access your podcasts, or at nakedscientists.com/reflections. Do join us next time.